Hey everyone. Let me know if you can hear me all right. I'll have the chat open on the side as always. Just let me know that everything looks okay on your end as it does on mine. And just a reminder, use the live chat during today's lesson. Hey Alan, hey Harold, awesome. Instead of the, well, you can use both. Ideally, I don't know. Now that I think about this, you can use either, I think. Basically, I'm going to take the QA parts. I didn't quite get there for the last video, but I'm just going to, I have them all written up and I'm going to put them in the description of the video. So you can put them in either the lesson 2 questions or lesson 2 chat or in the chat and I'll find them. Hope everyone's doing well. Just now got the lesson 1 needs to re-render, but lesson 1 now has the actual YouTube link embedded. Took me a little bit to figure out how to do that because Firefox changed a few things with their security. Volume seems a tad low. Is that a bit better? I might have accidentally placed my mic a bit too far. There's also like a 15 to 20 second delay on some of this. So internet's being rather fun today. Might just, yep, awesome. Thanks. Otherwise, today we're going over lesson 2, and it should not be nearly as long. Hey, Ron. Yeah, it should not be a 2-hour lesson. It should be, I'm hoping an hour. It'd be nice. Probably an hour and a half at the most. Because we're just focusing on one tiny chunk of the API today. I say tiny. Not really that tiny. Do let me know what you thought of the edited lecture for those of you that have watched it. What you think of how it's set up and if I edited it enough. Or if there were some parts you wish it had in didn't have. Feel free to throw that in on the poll that's sitting over in lesson 2 information. It has a couple stuff about that, so if you could fill that out, that would really help me with all of this. But otherwise, it is 101. So let's go ahead and get started, because I think that's probably everyone that's going to be live. All right. Hey, everyone. Welcome to lesson 2 of Walk with Fastai Revisited. Today, we're going to focus on the low-level API part of fastai. So in the previous lesson, we introduced that there's sort of 3 levels, almost 4 in some cases, depending on if you go by Jeremy's definition or mine, with the lowest level being the datasets. And we're going to take a full lesson to just talk about the low-level API from data, as well as integrating Pytorch, which is going to be a big jump, but I want this to be sooner rather than later to get you thinking on it. This notebook is, and this lesson is kind of designed so you come back to it a bit often. It's sort of like Jeremy's ladder lectures in that sense, but mostly because we're going to talk about a lot of the smaller parts of stripping away some of the framework as we go. And then every lesson after this will show the 3 different API levels or 2 different API levels between data block and datasets as we go through this all. So that way you can sort of understand oh, this is how this translates to that. This is why that works in this way, to sort of help with it. So the first part of today is basically going to be Jeremy's MNIST classifier. So if you remember, or if you've taken the previous Practical Deep Learning for Coders version 3, Jeremy's lesson 2 talked about MNIST. We're going to do something very similar, but teach it in a different sort of way. And then the second half of this lecture will be using raw Pytorch with the fastai learner. So let me know if I go too fast for anyone or we need to repeat a few steps, because this is going to be fairly information heavy. So in the last lesson, as I mentioned, we saw how the fastai API applies to cats and dogs and on a real Kaggle dataset. And today we're going to use the MNIST dataset instead. And for those unfamiliar, MNIST is the Hello World dataset for data science. It's handwritten digits from 0 to 9. To download it, we use our untarred data again and use the MNIST URL that is provided for us in the URL's namespace. And if we look at what it contains, we have we have two folders called training and testing that are stored away in some data cache that fastai uses. So in this case, we're going to be splitting based on these two folders. So let's take a bit further glance into these folders because we still need to know how we're labeling our data, right? So if I just view 10 of the items by doing get image files path, this will also, because the path is where we stored the data, as this little outcropping mentions here, it's going to get us all of the images from both training and testing. You could do path/training if you just wanted the training images. But it's nice to look at this because if training and testing both showed up here, it's just testing. But you can see if the data is set up the same without opening, say, File Explorer. So we can see that it's the set, whether it's train or test, followed by the class that it is. So this is the number 7, and then the image name. So let's try opening up an image using that low-level API. Last time we used pil.image directly, or pil.image as fastai wraps around it in those transforms. Reference back to the API overview in lesson 1, what is the fastai API? It has all of the different classes for vision, tabular, and text when it comes to the transforms that you should be very familiar with. So that way you're able to talk about, oh, this is what this is, and not just fastai's magic image worker. You can say the class and why it exists. So for working with black and white images, or 2-channel images, fastai has pil image black white, and then we call .create, which is a class function for every single transform that takes in some item we can open that it expects. So for pil black white, that's going to be like file name, some what's the word I want? Some raw data off of like a GET request, and even just a PIL black and white image itself, it can be created through this. And then after we create our image, so this is just one item. If we go back a little bit, we stored all of our file names and items. I'm just passing one in. We can call .show, which in the fastai data API, if it's a data class that I mentioned earlier, it has a .show function to see what it looks like. You can see that right now we have the number 7. Great. Next, we need to figure out how to split the dataset, which, as I mentioned earlier, we have a training folder and a testing folder. Fastai has a function or a class called the grandparent splitter, which imagine child, parent, grandparent, or I'll visualize this with the file name, that's easier. So we have child, parent, grandparent. So it will split based off of this third file name, also known as splitting by folders. And we just pass in the training set folder name and the validation folder set name. So as you can see here, then I go ahead and call our splitter. So we're removing that data block. Data block won't really be here too much. We're instead going to look at what each of these do. So this splitter, when you pass in an array, it can be an array of anything as long as the splitter is set up to process it. It will return two lists. So this first list is our training set, and the second list is our validation set. And these lists are indexes into whatever we passed in. So the 10,000th item in our list correlates to the first item in the training data set. And the first item in the list correlates to our validation data set, which is what we saw earlier when we were looking at the file names, and it showed testing as the first option. And then fastai will use this to then split the data on the fly when it's trying to create a data set, essentially. So it doesn't store the actual items separately. It just stores these splits. And then it's able to go like, okay, we're going to do the training data set. Training data set consists of all of these. I know to go and get those indexes. So we have 60,000 in our training data set and 10,000 in our validation. So the next step is to build what fastai calls a datasets object. Now, in a light scope, it's equivalent to torchutil's dataset. It does a bit more. So it takes in the splits itself, what we just made earlier, those two lists of indexes, which could have any number, fun fact. So if you have like, say, a train validation in a test, you can pass in 3 separate splits, and you can then access those items. I believe I'm showing this in a later lecture. But in order to use it, you pass in some items, as I mentioned earlier, our splits, and then lastly, some transforms. Now, these all look very different than the transforms we used last week, right? There's no resize, there's no aug transforms here. What's going on? The technical term for these is what's called type transforms. And what these do, they're designed to take in some individual item and then prepare it and open it to be then passed to any of our transforms, those augmentations I mentioned earlier. And I will try and be good about separating augmentation from transform, because every augmentation is a transform, but not every transform is an augmentation. So sorry if I slip, but I'm going to try my best not to. So here we pass in transforms that correlate to our X and our Y. So this goes based off of our, basically it's a list of transforms, with the first being the X, the second being the Y, and you can have this be, 2 different image inputs. So you could have PIL blackwhite.create, PIL blackwhite.create, and then the labels. This can be customized in any way, shape, and form. The data block also has a pass through to this. That is that N input I mentioned last week. So here we want to open that image like we did last time, a little bit earlier. So we want to do PIL image blackwhite.create. And then for the label, not the split, but the label existed in the folder that the file existed in. So we want to use the parent label function, which is what it's designed to be read as. And then categorize is what actually does the categorization, one-hot encoding, and so forth to the class. Is the order here controlled by what transform is placed first in the list? Yes. In this case, these transforms don't have a concept of order. So it's whatever you pass in is the pipeline that it will go. Because these can just be functions, right? PIL image black white is not a transform, it's a data type. And parent label is just a function as well. Now, categorize is technically a transform, I believe. So it has encodes and decodes and whatnot. But these don't have to care about an order. The order is based on how you order them in this array. So I mentioned earlier that we can request to see items based on their index through the train or validation set. We do this by calling, so in this case, I'm going to call it a data source. Technically, you could call it data set. Data source.train, so that way this is a subset of only those training indexes. When it goes to get an item, it knows to only look at the training sets. And show at is a fastai function that lets us decode anything that is sent in to our data source. So I can say, show me all of the transforms in a way that I can view it for the third item in our data source. So in our case, item number 3 is the number 7. We can see the X and the Y. Don't worry. Well, I guess we can go into that. That's okay. I believe that, yes. So don't forget to look on the code plus explanation as you're reading through this material. Because some of the stuff I won't explain 100%, but just to not repeat myself. But for today, I'll go through and explain every single transform and sort of what we're doing, because it is the lowest level of the API. So if we were to read sort of what this is doing, so we saw earlier that our X does PIL image black white.create. That's what we just did a moment ago. Now parent label, well, before we even get to that, snap for YouTube editing. So when we read these, it takes an item from our data set and throws that single item through all these transforms. So when we do data source.train at 3, it's going to take the third item, pass it through black white image.create, and return our black and white picture. Now it takes in the full file path for this particular part. So when we look at these two, parent label will return a string of the class name because it's in the file, right? So it's going to return the string 7, but we can't use strings in training. It needs to be numbers for us to be able to calculate like a loss. And so we need a way to encode that string number 7 into a number 7 where we also know what all of the potential classes are. Categorize does this for you. This is what we call label encoding. And so there's some fancy parts in Categorize that I'll probably show towards the end of the course in the fast core section. But basically all you need to know is Categorize understands how to take whatever you're passing in as a class and encode it in such a way that we can train on it, that it turns it into a number. This is the same with categorize, multi-categorization as well. Rohan, let me know if that answers your question. So now that we have the data point of 7 with a label of 7, we can then apply some transforms to it, right? Those item transforms that we had earlier. Now, you'll notice that this doesn't quite look the same, however, as what we had before. A, because it's a smaller data set. These are 28 by 28 pixel images. But on top of that, there's probably one here that you've never seen before. This 2 tensor. So this is called, when you do anything through the data block API, you don't actually see this occur ever, and you don't have to add it in. because fastai will do it for you. If you add it in multiple times, it doesn't affect anything, but it will do as it sounds, convert everything to a tensor. So that's how magically we take a pillow image and convert it into a Pytorch tensor. Now, the first thing I've done here is what is called pre-sizing. So that's where you make the image bigger. So that is what this crop pad 34 does. And then I perform a random crop back down to size 28. These are still with our PIL black-white images. And then we finally convert them from PIL images into Pytorch tensors, or fastai tensors would be another way to put it. And because they're item transforms, this is CPU bound, with the intention of making sure everything gets to be that same size. Afterwards, since it's a smaller data set, I don't have aug transforms in here, but we do have normalization and another new one, int to float tensor. In order to be computationally efficient and take full advantage of our GPUs, when training a model, you will convert the inputs into float tensors. Here, this converts them into integers. And so this is that's what int to float tensor does. And this is another one where you don't see it happening. This happens automatically through the data block API. And then normalize. Last time we did normalize from stats, right? Here, though, we're going to be removing all pre-trained models from our problem. So it is just building our own model, or at least having an untrained model, and building our own data set off of these random weights. So we don't have any normalization statistics. So instead, we will just call normalize itself. And as shown sort of over here, the way fastai handles normalization, and Sylvain and Jeremy did a chunk of research into this, you can get pretty close statistics on the full normalization data of your, or full normalization values for your data. So the mean and standard deviation by just looking at a one singular random batch, and it's close enough. And so that's what this will do. When you first build your data loaders down here, it will process one batch of data and figure out what those values are. A few other questions. Categorize actually assigns the same number as the string label suggests. No. So it assigns it based off of the index. I should have made that a bit clearer. So say we have cat, dog, and bird, right, as 3 classes. Sending them through categorize, it will alphabetize them first, and then assign them a number based on 0, 1, or 2 from that order. If we had augmentations, would they have been placed before or after the int to float tensor? So these item transforms and batch transforms are where the order in the transform takes over. So in this case, you could put it anywhere in here because fastai will reassign the values. If they're the same order, then it matters a bit more, but I could have, say, like int to float tensor, random resize crop GPU, and then normalize. Now, that's not readable, though, so to keep your code clean, put it before the int to float tensor. And you could even create a separate array called augmentations that you store that in as well, if you wanted to. But that's getting into the nitty-gritty of API design and clean code, which is very, very important, I will add. Why is int to float tensor in the batch transforms and not the item transforms? Because this usually will happen on the GPU. In general, that's why we convert to floats. And then on top of that, it is more efficient for us to turn them all into floats on the GPU in a batch all at once than do that all on the CPU one at a time, essentially. And on top of that, int to float tensor is the first of the batch transforms to ever be called. If you go through and look at any of the image augmentations, since most of this is related to vision, all of them typically that are assigned as a batch transform have an order after int to float tensor. So Yeah, I guess we can look at that. Why not? That is a bit important. So let's go through and show you a bit what I mean. So like if we go to data transforms to get into float tensor, and then I'll zoom in a bit so you guys can actually see what's going on here. And then if we go to vision and augment, so I do not want this. If I go all the way down, somewhere in here should be into float tensor. So you can see into float tensor has an order of 10 with a comment, a very rare comment, of needs to run after PIL transforms. So that's the pillow transforms that happen on the CPU, on the GPU. So it has an order of 10. Now if we go to the vision transforms, and we go and look at, say, what would be a good one that actually describes what we have? That's right, because these are all item transforms. If we look at random resize crop GPU, you can see it has an order of 30 to make sure it happens after into float tensor. And also, so if you have anything that needs to happen before the vision transforms, there's a variety of numbers available to you in the order to put them in. And then the last thing you'll notice is normalize has an order of 99. This is because normalization should always be the very last transform you do. If you have something that has to happen after normalize, though, of course, you just have an order of 100 or more. Hopefully that helped make things a little more sensible. All right, so the last step, similar to what I showed in the data block API yesterday, is we call .data loaders, passing in a batch size, as well as our item transforms and batch transforms. Now, I have a little warning down here. You'll notice that I called them item and batch transforms in the name of the objects, as well as we pass them in as batch and item transforms in the data block. But when it comes to data sets in the lower APIs, it calls them after item and after batch. For now, just understand they're always referred to as this because they are called after an item is opened, and then after a batch is collated. So you take 64 images and turn them into a single batch. For now, just understand that's why the name difference is there. But don't use them interchangeably. So you can't say item transforms equals blank when calling from datasets, and you can't say after item equals blank in the data block. fastai should raise an error for that. At least I hope it does. So now that we've checked our augmentations and passed that in, we can still call show batch, because at this point, this is just a set of data loaders, just like how we would build off of the data block API. So we have our image, 0, our label, 0, an image of 6, label of 6, and so forth. And so this looks, much more familiar. We're ready to go on our way. Now let's talk a bit more about some more ideas behind training and what we're actually doing. So in order to get one batch of data that is fully pre-processed through the data loader, you call dataloaders.oneBatch. And for the sake of naming, XB will be XBatch, YB will be YBatch. One thing to note about this is, where was I going with this? Yes. One thing to note about this is when we call dls.oneBatch, this will by default be the training data set, I want to say. And so you would, to specify which data set to do, you would call like dls.train.oneBatch. As for the sake of when it's at the data loader's point, train and valid now mean the train data loader, the valid data loader, or validation data loader fully. Now with this, we can do a number of things. We can look at the shape of it because they're tensors at this point. So our data set is for one batch, which we said was 128 items, is 128 by a single channel by 28 by 28 pixels. And then our labels is an array of 128 numbers because we encoded the labels to be somewhere between 0 and 9, right? Based off of what they were labeled as. The last thing is, remember how I said that categorize will go through and figure out how many items you have in your data set and so forth? As a result of doing it, we get this new attribute called dls.c, or .classes, which in our case we have 10. Now, one thing to note about when you call .data loaders here is the way it figured out all that information is when you call data loaders, it will run through one pass of your data. So it'll get one batch and calculate a bunch of things. And what it does when calculating it is it will figure out and set up how many training classes do you have. This is set up in the data source as well when you call it. So like for instance, when we call data source or data sets, right? When we built our data set, it ran through the setup configuration. We'll call it setup configuration for now. Saw that categorize has one and went through and based on our items, figured out how many classes they are and what name they have. And for the batch transforms, when we did that down here, it figured out what our normalization statistic should be off of one batch of data. This is so that first you can dummy check to make sure that all your transforms are working properly, and B, to figure out what those values should be during that setup portion. So that's how we can get away with normalize, and it'll magically be able to figure out what our statistics are the moment we build the object. And it essentially calls dls.onebatch internally to start doing that iteration. There's a question of, when calling one batch a couple times, will it return the same batch or will it mess with the data loaders? Yes. There was a second part to that of like how iter and next will get the next one. Basically in that sense. So if what I will do is open up a new, actually, no, I guess we could do this. And this would be important and good. So this is a very good question, and it's not something that's easily shown on the course page. It's much better if we iterate. So I've just opened up a Scratchpad notebook, and I'm going to do from fastai.vision.all import star. Now, one of the things I have bookmarked, not sure if it's still bookmarked in here, but if we go to, I guess really docs.fast.ai, examples, app examples. This is a notebook hidden away in the FastAI docs that has a whole bunch of cut and paste examples for you to quickly use. It's using the highest level data block for a lot of it, right? The XYZ from name or something. But it's great for situations like this when you want to explore some things. So let's answer the question of how one batch might return different things by quickly building a data loader and exploring this, because it doesn't matter what we use. We just want to know about the order of things. And what the question is referencing here is when we were training on our data last week, every time you did an iteration over the data loader where we did one epoch, the training data got shuffled. So it was never in the same order, and the validation data did not. So if we do data equals dls.one batch, and then data2 equals dls.1 batch. And we do like data 0, which will get us our, well, actually, I guess we could do data 1, which will get us our labels. And then the first instance of it. So here we have a tensor category of 0. And if we do data 1 at, say, or data 2, its first label is 0 as well. Now, if we go to a random number, it's 64, sorry. So we'll go to the last one. You'll see it also has the same. And the reason for that is dls.1 batch returns based off of the validation set. So when you call this, it's going to be the same every time because the validation data doesn't get shuffled. But if we were to say do train, right? So this is dls.train.1 batch repeated. Now they're different because every time we call one batch, technically it does what the commenter mentioned of next iter dls.train, which in Python says the thing I'm passing in is something we can iterate over, like say in a for loop. I want to get the next item from this iterable thing. And so if we run this quickly, right, it's going to get us a batch of data. And if I run it again, because we have a new iterable object, fastai will technically shuffle all the data in it. And so that's why this is magically different. Whereas if I did something like, well, I guess that doesn't really work. But does this make sense? Sort of what I showed. It's a bit more advanced. I think I'm going to talk about this a bit more in one of the lessons. It might be the next part of this lesson. But it's a good thing to know, especially for like Python and how Python operates. But that was a very, very good question. I'll leave this up in a tab in case we want to go back to it. If there's any other questions with that, feel free to let me know. So the next part is, so we've built these data loaders, right? And we've added these transforms to it. We have this data and it's 2-channel black and white images. The next part we're going to do is build a model and train, right? Step 1, step 2. In this case, we're going to use our ResNet 18, similar to the ResNet 34, but think of it as a smaller model. Now, for this particular problem, we're not going to use Vision Learner because I want to show you raw Pytorch and fastai as much as I can here. And as I mentioned before, we're not going to use a pre-trained model. So instead, these are just going to be completely randomly initialized model weights. So every weight is randomly set at some starting point. To do so, we call ResNet 18, which this is actually from Pytorch. It's not, or really from Torch Vision. It's not something fastai has. We pass in the number of classes to use, which will be dls.c. And then for the sake of simplicity, I turn the model onto the GPU. That's what this .cuda does. And then finally, model.fc is the final classifier layer of the ResNet 18 model. This is without us removing the head of the model. So none of that's going to happen in this lesson. And we can see the last layer is a linear layer that takes in 512 data points and returns 10. Don't worry much for right now what linear does. I'm not really going to talk about that in this course a whole lot. Just for now, understand my out features matches what my expected should be, and that's good. Now, however, is that enough? So ResNet 18 and ResNet 34 were trained on 3-channel images, right? Because we had RGB, and now we have 2-channel images, or really a single channel of black-white. And so if we say take a batch from earlier and pass it to our pass it through our model, we'll get this runtime error. Given groups equals 1, weight size of some weird thing, expected inputs of this to have 3 channels, but got a single channel instead. And essentially what that means is exactly as I stated earlier. This model expects a 3-channel image. We gave it a 1-channel image. So how can we make this work well? Let's look at this layer that's giving us issues. And in this model, it's called conv1 or convolutional layer 1. And it's a conv 2D layer that takes in 3 with a filter size of 64, some kernel size things, some stride things, some padding thing, and something about bias. For us to care about, the main thing here is this is our input channels, this is our output channels. So we need to make this become a 1. And we just do that by assigning a new conv layer and in conv2d, take all these values, plug them in, and change the input channel to 1. Now, this is a very quick and dirty way of doing this. There's a variety of other ways to, say, maintain the pre-trained weights that came along with this if we were training from a pre-trained model. There are resources on the fastai forum if you do some digging on how to approach this. Usually what you wind up doing is you take these 3 channels and you average them together into 1, and that is your weights for the single channel conv layer. Now we can try it again, change all of our weights to CUDA, and we can see that it successfully was able to process a batch of data. Now, there's a little note here of actually what that looks like, of what that code looks like to store the weights and reuse them. So feel free to look at that, but that's a bit out of scope for today's lecture. And all that's left now is to build a learner. So remember how in the last lesson I told you we have functions that create learners, but they're not themselves learners. So like vision learner, tabular learner, text learner. These are functions that build this learner class through a lot of other pre-processing and magic. So today we're just going to use the learner class, and it takes in a lot of the same values as what we pass to, say, CN and learner. So we pass in a set of data loaders. In this case, a fully completed Pytorch model and some metrics to train on. This looks almost indistinguishable from what I presented yesterday. And then just like before, we can call any fit function we want. Now in this case, I'm just going to call fit, which has no scheduling or anything. It's just iterating through the batches, send it through the optimizer, and you're on your way. This should be extremely quick for you when you're running it. MNIST doesn't take a lot of time to train. We can see training loss is lower than the validation loss, which is good. We're overfitting. And our accuracy is about 95%. That's not bad in a single epoch. You'll notice a lot of people will approach 99 or 98 and say they have a new state-of-the-art. Fun little tidbit about that. MNIST actually has some dirty data. So by how everyone's doing metrics, this never actually will hit 100%. If it does, then you're terribly overfitting. All right, so we have a model that can classify some handwritten digits, right? Now, how do we do inference? Because I did not show you this yesterday. I sort of left it to your own devices of train a model. We'll do inference today. fastai has a number of ways to do predictions. The highest level version of it is a function called learn.predict. It takes in an item, a singular item. This is meant for only one individual value. And it works by having this item be the same thing that that type transform entered earlier. So remember how we had PIL blackwhite.create? This item needs to be something that PIL blackwhite can do something with. And in return, we have the string representation of whatever it thought that was. The tensor representation, so that number, right? So this is the unencoded, this is the encoded value. And lastly, our predictions. So this is the raw probabilities of, and I think they're summed up to 1, I want to say, of each class. So like this would represent the probability of class 0. This represents the probability of class 1, 2, 3, and so forth. So it said it was 7. So if we go 0, 1, 2, 3, 4, 5, 6, and 7, this had the highest value, right? Because when we think E-1, so that's going to be 0.89. That had the highest value, so it thought it was 7. Which it was correct in thinking that. Now let's get a bit more into what it's doing. Now, I need to include some annotations for this, I think, and at one point I thought I did. But under the hood, learn.predict does something that looks a lot like this. And it's a lot to take in. I'll walk through some of it. And because there's a lot of parts of predict you don't necessarily need. And there's a lot of stuff fastai wraps over. And so in later lessons, I'll show you how to do predictions without fastai transforms at all, really. But the basic concepts to ensure you understand is, remember I said there was 2 ways to do predictions. The first is predict. The second one is learn.getPreds, which this is how fastai gets all of our predictions with any data loader during training, validation, so forth. To create a new data loader that is built on our validation transforms, you call the testDL, test data loader, function. It will create a new data loader that is fully set with our validation transforms for whatever you pass in. Now, since predict takes a single item, if you look at the source code for predict, it's going to show something like the following, because we're only taking in a single item and testDL expects a list. But if you were doing this outside predict, you could pass in the entirety of items, for instance. Now, when we're ready to get our predictions, fastai will call getPreds, pass in the data loader, what is called with decoded, and in this case, it translates to with the loss function decoding their values. Don't worry too much about that. I'll have explicit notes in here later today of what all of this means I'm talking about. But in this case, remember how this was already summed up to 1, right? They're not the raw probabilities, they're the soft-maxed probabilities, where rather than it being everything at once, they add up to 1. That is what, for this loss function, that decoded means. This does not mean fully decode my output. And then with input, fairly straightforward, return the inputs. And then it returns a number of things. We just care about the inputs, the predictions, and the loss function decoded predictions. I know that's a lot of information, so I'm going to take a second. Before we move on to the third line of code here. So the last part is this decoded based off of the loss function because it's tied to our learner. And we returned our inputs as well. The last part we need to do is take these decoded outputs that the loss function gave us and send them through the data loaders to reverse our transforms back until there's something showable. So this is what image and class prediction are. So we use what is called data loaders dot decode batch because we want to decode a batch of data, even if it is a batch of 1. It takes in a tuple of our inputs and a detupled tuple of our decoded predictions. This is what it'll look like in the fastai source code. Tuplify just means turn whatever we passed in into a tuple. It's kind of the same thing as this, but if it's already a tuple, it won't do anything. And then return the first thing back from that, which will be our image in our class prediction. This is super advanced fastai stuff. I sort of put it at the mid level in difficulty between it and using raw Pytorch itself. If this doesn't really matter to you per se, and you're fine doing your own post-processing, I highly recommend doing that instead. But this is what learn.predict does under the hood in a way to sort of help you understand why is it just 3 lines of code and what the heck does it mean. So next part we're going to do is strip all this away, right? So we're not going to use raw Pytorch for this per se, for the transforms and decoding. We're going to use FastAI's transforms for us. Just because it's using raw Pytorch is something we'll get into in lesson 5. That's very heavy on top of this already heavy chunk. But let's go through sort of what this looks like. So remember I said that the transforms are not stored in item and batch transforms. They are called after item and after batch. So we can look, see that they're this weird pipeline class, crop pad, followed by a random crop, followed by toTensor, like we expect, into float tensor, into normalize, and we're done. And it's got some nice information about what that transform does. So like our crop pad had a size of 3434, or our normalize did not have a mean or standard deviation explicitly passed. This still has our data stored in it, which you can see here. If I go through, grab the second transform in our batch transforms, which we know is normalize, we can see the mean and standard deviation right here. This is what FastAI calculated off of a single batch of 128 of our pictures. So now that we have all this, let's strap away our data loaders and recreate what we did using FastAI's interesting pipeline class here. And pipeline just means a list that acts, as you'd imagine, a pipe. So you take one value, send it in, and it goes through every single value in this pipeline, organized by transform order. So this is why that transform order is very important. And on top of that, you can also adjust whether you want the train or validation augmentation to apply, because there's no separate crop pad for train versus validation. The behavior is actually thrown into its implementation. Someone mentioned that's very useful for writing your own prediction functions, this little snippet here. It is. I highly recommend, though, that you skip ahead and look at lesson 5. Deploying without FastAI is going to be the most useful snippet for doing inference with FastAI ever. Because I've completely stripped FastAI from it. And that's one of the hardest things to do with this API for the validation transforms. So now let's create our type transforms, our item transforms, and our batch transforms. Now, if something doesn't have an order, the order doesn't actually take into effect here. So we have our PIL image, black, white, create, our cropping, and then our batch transforms. So we can see that I mentioned, a pipeline takes it in, spits it out. We pass in a path, it gets us a PIL image, black, white. We pass in our item transforms, it gives us a 1 by 28 by 28 cropped tensor. And then if we pass in our item transforms, and because the batch transforms happen on the GPU, we have to call CUDA. If we pass them through, we see that we get a batch of 1. And yes, these will have explanation tabs for all of this, or at least most of this, especially this part. Not 100% sure why it doesn't have it. I seem to recall actually doing it. So that'll be live end of day today. So now that we have a way that we know how to get a batch of fully fastai preprocessed data, let's look at how we then get inference using Pytorch. So in fastai, our Pytorch model is stored in the attribute learn.model. And you did hear me right. fastai models are just Pytorch models. There's nothing special about them fastai specific in the sense of they can't be used in Pytorch because fastai is built on Pytorch. Next, we need to set it to evaluation mode because we are doing inference, and some models care about, or some layers care about if you're in training or validation for some of what they do. We'll create an object called TIM, which means transformed image. Do the same thing we did a second ago, which is get some preprocessed data. And then lastly, we use this weird context manager in Pytorch called Torch Nograd. And again, all of this I'll run through and add explanations for. And essentially what this means is when we were training, we got the outputs, put them through a loss function, and then updated the weights of that model by using something called the gradients. Now, because we're doing inference, we don't actually care about this magical gradients thing. And so as a result, we can just say with torch nograd, which tells Pytorch, okay, any model that gets an input from here on out, I'm not going to track its gradients. It's not going to do anything with the loss function. Nothing like that is going to happen. And get us our outputs. Next, the last step here is to get our class label and those probabilities we had a second ago. To do that, we call argmax, which looks at all of these predictions and finds what is the biggest in each of them. And for dim and stuff like that, I have a good notebook from Jeremy's part 2 that showcases what all of these do with dim, and I'll link to that in the Discord. But we can see that it says, okay, this is a label of 7, which in our case, because it's 1 to 1, it is the actual label 7 and not just the 7th or the 8th label in our list. And then in order to get the quote unquote probabilities, where we have everything be a percentage sum up to 1, so like what percent is it of label 7 versus label 6 versus label 5, we do what's called softmaxing and specifying the first dimension again, or the last dimension. Technically is what -1 means here. So that was a lot. That was a lot. But this is sort of what I want to get you thinking about as we go through the course, because it's going to help build the foundations for running with fastai. And even if you don't do running with fastai, getting familiar with this will make you a much better fastai programmer as well. Now we're going to take a 10-minute break, and then we will go over to the second part of the lesson using raw Pytorch and completely removing all of fastai, except for a few chunks. So feel free to drop any questions you have. I'll answer them when we get back. But yeah, feel free to do whatever you want for 10 minutes. There we go. All right. Let's see. Did we have any questions that are worth? Yeah. So someone asked what the difference is between a sorry. Someone asked what the difference was between an augmentation and a transform. And essentially, the way to think about that is transforms take an input and modify it. Right, so like normalization is a transform because we take, say, a set of numbers and we use statistics to normalize them into like a bell curve. Whereas an augmentation is something only applied on the training data set to make the images more unique or different and more challenging. That's going to be things like randomly cropping the image at a random point or adjusting the brightness for the image. So the augmentations are things that only apply to the training data set. Transforms is something that takes an input and modifies it overall. So as a result, every augmentation is a transform, but not every transform is an augmentation. Sorry, hopefully that makes sense. And that was the main one I saw because the other one posted there we're actually going to get into. So, next up, we're going to look at getting a bit more complex. We're going to completely remove the data API. More specifically, we have 3 rules. So we can't use the data API at all. It must be raw Pytorch, except for, I think I allow some transforms, but we can't use like the datasets class. We can't use Vision Learner. We have to create our own model. And then another thing that sneakily Learner did for us is it created an Atom optimizer for us. We're not going to use that. We must use a Pytorch optimizer. And if you're not quite sure what an optimizer is or anything like that, I'm going to cover that in this lecture as well. So more meaty lecture for us here. Now, everything that's going to be done here has explicit imports. We're not going to do import star, I think, at least for this first part. I don't think I do it later on. Yeah. So we're going to import the only fastai functions that we're allowed to use, which is bringing in the data. That's going to be untarred data in URLs, the normalization statistics to do normalizing, and then we'll import pathlib's path from fastcore. And there's a little comment here. So fastai does a lot of monkey patching, which I believe I mentioned last lecture. And importing like this will bring all of that monkey patching in directly. I prefer this sort of syntax when importing. There's another syntax where you just import the module instead and explicitly state pathlib and importing it. There's 2 different ways. This one I find a bit better and clear. Now for this problem, we're not going to do low level with MNIST because that's 2-channel images. There's not a whole lot we can do with it in that sense. We're instead going to go back to pets. And you'll notice throughout this course that pets is basically going to be our fallback data set because the main goal with this course is, while I want you to get familiar with different APIs and different segments for training, like computer vision versus segmentation, it's really more understanding fastai. So that's why, you know, there's not going to be object detection in this course, or why there's not going to be style transfer in this course. Those are for Walk with fastai original. We're going to talk more about, let's understand this one data set very well and use fastai in a million different ways around it. So very quickly, if we look at ImageNet stats, it is 2 arrays. which is our normalization statistics for 3-channel images, right? So this is the mean for channel 1, the standard deviation for channel 1, 2, 2, 3, and 3. Now that we have all of those, I'm pausing because I might get interrupted by my cat. We'll find out. He is now on the table. What we're going to try and do is get close enough to how fastai does its transforms with torch vision. Now, it's not going to be perfect. Lesson 5 is going to go really in depth as to why it's not perfect. So, sorry for the random scrolling. But basically, our transforms that I showed earlier are boiled down to randomly resize a tensor or a picture to 224 by 224, convert it to a tensor, perform some more data augmentation like lighting and transform and rotation, convert it to a float. Technically, this happens before then, I believe. And then normalize it based on our pre-trained weights. For simplicity, I've just shown all of this here. Pytorch has a layer, like a model layer, called nn.sequential, which, if you remember back from the previous lesson, I mentioned our custom head also kind of worked in this way, where essentially it reads as a pipeline. So this would be sort of equivalent to fastai pipeline, where it goes, okay, this is the first, this is the second, except the order in which this is built matters. Now, the other thing is, you'll notice I import center crop, random resized crop, 2tensor, and normalize. 2tensor is going to happen before we do anything, which is why we just resize and then normalize. And you'll also notice, well, first, that this is all going to happen individually, right? Because there's no item transforms happening here. It's just resize and normalize. The second thing to notice is I have resized random crop in my train and center crop in my validation. It's not the same because fastai doesn't operate in this way. So what fastai will do, and this is that difference between augmentation versus transform, randomly resizing and cropping to a particular size is an augmentation. Center cropping is a transform. And what I mean by this is when the validation set is called through transforms, you don't want to randomly lose some data, right? When you're doing inference, all that data matters. It doesn't matter as much during training because we can get, different images, different pictures for every time we do an iteration based off of one image. But during production, we don't. Every single pixel matters. And so fastai does what's called a center crop, or center crop with padding, so that it's just showing the middle of the image with all of its context there. And so that's sort of why train transforms looks a bit different than valid transforms. Now, the next thing is we need to make a Pytorch dataset. Now, to create a dataset, this is kind of going to go into Python a little bit. We need a class that has 3 functions. And a init, this is what we call a class constructor. So that's what happens when you do some class parentheses. It creates the object by calling its constructor. For our particular class here, since we want to create the same dataset that we've kind of been doing the whole time, it needs to take in file names, some transforms and augmentations, and a way for us to turn the label strings into a number. So doing that label encoding. The next thing it needs is a length. And this is so we know how many items are in the data set. And so this then lets us know how many batches are in the data set, and fastai needs that information. And then finally, we need what's called a getItem function. And basically what that does is, say when you do list at index, what it does is it calls getItem, and getItem goes, okay, you want this particular item. I have my own implementation to say, let's get X item in the list, and it'll return that for you. But without having to call get item, it just does that automatically for you. Now, the class for this is basically ripped off of, you could say, but it's highly based off of Sylvain Guger's example from Accelerate. I've included a link there because the examples in Accelerate use pets. It's a great way to approach it. Now, this does have code and explanation for you, so I'll very briefly go over what's happening. So as I mentioned before, we store the file names in a list, our transforms, which we'll expect to be some sort of NN sequential, and some way to convert our labels into integers. In our case, it's just going to be a dictionary. And then there's two functions here, apply X transforms and apply Y transforms. So this will apply the augmentations and transforms for our X values based on some file name. This goes through, opens the file in Pillow, converts it to a tensor, and then applies the transforms. And then similarly, we need to take our file name and get the Y's as well. So this is back to that regex part, that fastai I did before. Convert it to lowercase, and then index that dictionary for the right label. There was a question of what is a good way to include vocab2 in our dataset? You could add a property function, but really in this case, label2int sort of acts as your classes. So you could return like label2int.keys or .values, depending on how you set up, because that will just return all of your classes. So finally, we need the get item, which get item takes in the index we want to approach. And so from this, we'll get the file name at that particular index, apply the X transforms to it, apply the Y transforms to it, and return a tuple of the input and the output, or input and expected output. There we go. So as I mentioned, there's a code and explanation tab here. The explanation goes fairly in depth, somewhat as to what each of these chunks do. But this is a sort of light rendition of how fastai does its transforms, if you were to rip away all of the magic that datasets does. Now, the other thing is this is one data set. So we will need one for training and validation separately, which is why we just call it transforms and not train transforms and validation transforms, for instance, because we had two different sets of transforms earlier that we made. Now let's do a bit of prep work, as we're not using fastai to do things magically for us. We need to get a dictionary of those labels, right, to encode our classes that I just mentioned we pass in earlier. And then we also need to split the dataset randomly 80-20. So this is mostly so that we can define our label to integer. Because if you notice, we have this here as well. That's the main reason for this one. So we'll get the label pattern, and we'll get all of our file names. And then based on all of that, we can use a bit of Python magic, because this is not a normal list. It is something called an L, thanks to this .ls that I have here. And the way to read this is pathlib object, add in images to the end of it. Based on this new object we made, call ls and get me all JPEGs from it. So now we have an L list of file names, and I can call .map on them, which map says, give me a function, and I will apply it to every single item in that list. So here I'm just saying, using regex in our label pattern, get me the name of the class. And then at the end, I call .unique, so that way I can get every single unique class name. This is our list of classes. This is also what fastai does under the hood when you did that first .data loaders and building the data set that I mentioned, where it goes through and does all this automatically to find our number of classes and the vocab and so forth, and set up like our normalization. So here we can see we have a list of 37 labels. That sounds about right. The last thing we need to do is say, hey, for our labels, I want to be able to get them converted to integers. So here I just generate a dictionary by iterating over our labels. Now, enumerate, rather than doing this in a for loop of like for label in labels, enumerate will iterate over this list with the index and the key. This is a bit backwards here, but first it returns the index in the list and then the value that it had. And so what I have here is a way for, that's why I did that. A way for us to basically then go, okay, label to integer Siamese in our dictionary, and it returns me the number 36, which is what our encoded label is. Now we have a way to convert our labels into numbers, but we still need a way to split the data set randomly between 80-20. This is going to be a little bit more work, so we're going to use NumPy here. We're going to say, give me a random permutation from 0 to the length of my file names. And then I'll say the first 80% of those numbers is my training data set. And then I can get those indexes like we had earlier. This has code and explanation, so feel free to go and dig into that if this confuses you at all, or its Python syntax is a bit confusing. And then lastly, we can get our training file names and our validation file names by just getting from those indexes. After we've done all this, we can now create our data sets. So we'll create a train data set and a valid data set by passing in the train or validation file names, the train and validation transforms, and the same label to integer class setup to both of them. In fastai, it bases it solely off of the training data set, which is why I've repeated them both here. What can easily happen in that case is, say, magically one of your classes is so rare in, like, say, a set of 10,000 is only 5 of them. It doesn't make it into the validation set. Sometimes you'll get a key error that says, hey, this key that you're trying to predict on, it's not actually here. What happened? And that's because of how fastai builds this vocab for you to do things in. So if you ever hit that, you can explicitly pass in a vocabulary for fastai to use. Fun fact. Now back to this, we can look at one of the items in our data set using that get item. And we see that it's an image or a tensor of 224 by 224 with 3 channels and a label of 3. Now this says class label is 6. This is based on when I ran it, and I probably reran this just to make sure everything was fine. Now we have a data set. The good news is it's a lot easier now for us to create data loaders because all the transforms happened at the dataset level, which means it happened on the CPU. So to create a data loader, we import from torchutils.data, import data loader. We create a train data loader by passing in the dataset, whether or not the data should be shuffled. Drop last, which fastai also sets by default, basically states, if my last batch, even though I have a batch size of 64, is, say, 63 or 8, I want to drop that batch and not really train on it. It might get there eventually because we're shuffling the data as we go, every iteration, but I don't want to do that. And the reason that this is commonly done is it's a lot faster during training to have full batch sizes rather than partials. And then we create the validation data loader, which we don't want to drop last nor shuffle. So we keep the defaults, pass in our data set and the batch size. Now you'll notice that the batch size here is 2x of what the training data loader is. This is because here we have those gradients I briefly mentioned earlier that get calculated. In here we don't. As a result, we can process a healthy chunk of more images. Now the last thing to do, and we're going to start bringing in fastai code here, is to have it work with fastai's learner. We import their data loaders class. And this takes in any number of data loaders. So in our case, we have 2, right? Train and validation. And we just pass that in. What this then sets is this data loader is set to dls.train. This data loader is set to dls.valid. And fastai can work with that. All right, next, we're going to create a Pytorch model. Now, rather than last time when we didn't use a pre-trained model and we used a ResNet 18, we're using the normalization statistics. So we're going to create a ResNet 34, say we do want it pre-trained, and when fastai imports this magically, this is really what it's doing. It's saying from torchvision.models import ResNet 34. Afterwards, we need to create that last linear layer that I showed earlier when we were looking at the MNIST classifier. So it's going to take 512 inputs and output 37 classes. And there we go. Legally, we have everything to train on and we could go on our way. But we need to talk about something called gradual unfreezing. And I noticed that this is overcropping that a bit. I'll see if I can fix that. Well, let's talk about what gradual unfreezing is, first of all. So the general idea is when we created a model through Vision Learner, it cut off that FC layer as well as the pooling layer just above that to create what's called a body. Or the body of the model. Then fastai used a function called createHead, which created a new head for our model that we slap onto this body. And then finally, we did what's called freezing the backbone of the model, or that body, where all of those parameters that we had in this body are considered untrainable. Now here's a visualization sort of what I mean. So we start here with the original model, this body, and then what we will call this model's head. So it's a pooling layer and a final linear layer. And our new model that fastai creates has the body and a custom head with a new pooling layer and some other neat layers scattered in between, like something called a flattening layer, a chain of batch normalization, dropout, and a linear layer, similar to this final linear layer. For now, just know empirically this has been found to work a bit better in more situations. This will be something I might get into more in running with fastai, but Jeremy's course is Jeremy's part 2 is a good course on sort of what's happening here. Now, here we're not going to create a head. Creating a custom head and recreating all that from scratch is later on. That's lesson 5. But instead what we're going to do is still perform the freezing. So you can get all of the layers of a model by looking at .children. And if you convert it to a list, it gives you all of them in essentially order. So if I grab the last one here, you can see it's our linear layer like we had before. So what we want to do is for every layer in all of our layers, except for this linear layer, if it is possible to be trained. So that is what this requires grad does. Remember how we had no grad? Requires grad just means its gradients get tracked. If that particular layer has some sort of gradients that we want to keep track of, set that to false. Now, pooling layers don't matter here because they don't train. They're just a fixed equation that runs over our input and output and does a computation, but that's it. So with 3 lines of code, we've now mimicked what fastai does in CNN Learner, and technically the equivalent would be learn.freeze. Because the other side of that is learn.unfreeze. And so fastai calls learn.freeze on its own when you create it through one of those functions. Learner does not, though. All right, so we've frozen our backbone. The last thing we need to do is create a Pytorch optimizer. Now, what is an optimizer, though? I've mentioned this a few times. It is kind of one of the most important parts of our training. It goes through and, through a variety of high-level math, calculates how to update the weights of our model relative to the calculated loss for a particular batch. By default, fastai uses the AtomW optimizer. This is a little confusing, but fastai calls it Atom in the codebase. And so we'll import it and use it here. So from torch.optim, import AtomW. Next, to use it in the framework, we make use of something called an optim wrapper, which converts a Pytorch optimizer into something fastai can use. So this requires 2 imports by saying from fastai.optimizer import optim wrapper, and using a bit of Python, import partial from functools. Partial functions basically say, given some class or some function, I'm going to overload the parameters. So in layman's terms, before we had this optim wrapper class that takes in a variety of different things, including an opt parameter. We create a new partial function called optfunc. And when I call optfunc, I no longer have to pass in the opt parameter. It is automatically set to AtomW. Now, that was a lot. We'll take a quick 5-minute break. I'm going to try and introduce a few more breaks into all this, especially considering the level that we're going into. So we'll take a quick 4 to 5 minute break and let you guys sort of digest everything. Feel free to throw any comments you have and questions about anything I just showed. But we'll sort of resume recorded content at 2:30, 2:40, but I won't stop the stream, and this time I'll just stay here. All right, we took a bit of a break. Let's see if we had any questions. Looks like one was, what does the pooling layer do? I can link some docs in the lesson 2 chat, but basically it's a way for us to take a very, very large matrix and compress it down into something much smaller. So say it takes a like 128 by 128 by 128 matrix and compresses that down with keeping fairly useful data only to something much smaller that we can then pass through a linear layer and get probabilities off of, or logits. I assume the plane learner has a freeze function too. We just have to pass the splitter instead of manually freezing. Yes, we're going to look at that in lesson 5. But yes, the learner has a freeze function, and while I don't use it here, I will use it later. All right, so let's bring in fastai and do some training. Maybe. Just so you guys understand what just happened here, and I'll edit this out of the video. I might not. We'll see. In today's episode of How Does My Cat Want to Get Involved in the Lecture, he is currently asleep on the keyboard. So that is why we randomly had scrolling. Let's see. Maybe something like this, where I'll leave you over here and there we go. Hack the system a bit. All right, back to what we're doing. And you can't see over here, but it's scrolling up and down continuously. So, bringing in fastai in training. Now that we've created an optimizer, we have a set of data loaders, and we have a model, we have everything we need to train. So let's talk about what happens next. Or at least everything we need to train that isn't defined from fastai that we can use. So next what we want to do is use the... Sorry, I'm completely blanking over here for a moment. Give me just a second. To change something real quick. Sorry. I forgot to close something and it was sending me notifications. All right. So, as I was saying, we're going to bring in 3 different classes and functions from fastai. We're going to bring in the learner. You'll see there's 2 imports for the fastai learner here. This is because, as I mentioned earlier, we can do this sort of import to get patched functionalities. So in fastai.callback.schedule, this is where stuff like fit1cycle and lrfind exist. And then we'll import the accuracy function from fastai.metrics, so we don't have to write that ourselves. And then lastly, we'll bring in the cross-entropy loss flat class from fastai.losses. So now that we have all of that, we can create a learner, which looks like so. So we pass in the data loaders, the model, our newly created optimizer function, the loss function we want to use, and our metrics. Afterwards, we train just like normal. So we can call lrfind, get a suggested loss, which looks like 1e-3, and train for a bit on that. Now we get to about 88%, and you'll notice I did not call freeze. This is because we'll do gradual unfreezing in a later lesson. Today's just getting you used to training in general and starting to strip away fastai. So we have a trained model. Now we need to get predictions. Actually, before then, there was a question of how is it that we are importing to learner classes? Is it monkey patching? So this is how I like to define monkey patches. I mentioned this earlier when we were looking at pathlib, where I will do like from pathlib import path, for example, and then I'll also do from fastai or from fastcore.extras import path. And this is to show the main class exists in learner, and I'm bringing in stuff from schedule along with a comment next to it showing what we bring in. I just like how much Jeremy uses monkey patching. It's a terrible, terrible design practice, especially when combined with import star, because it disrupts the code base and you don't know where anything is. And so this is my attempt to make that easier to track. So it's purely for documentation purposes. Technically, this part doesn't need to exist, and we can just do from fastai.callback to schedule import learner. This doesn't need to exist, but it makes your code easier to read combined with comments for people who aren't used to fastai. And it will give you much less flack than doing from fastai.vision.allimportstar. Let's see. Actually, yeah, it's just a window. So you guys shouldn't see the notifications. It's just bothering me. So next, let's talk about how do we get predictions for our stuff. Once we have a trained model, we will open one of our images using pilimage.open again. Right, so here we have a picture of a nice, cute puppy. Then, like before, we will extract the trained model from our learner, so learn.model. And then we'll apply our validation transforms to the image. Now here, we'll just apply what we did before when we create our validation transforms. That's going to be toTensor in the image and unsqueezed. Now what I'm blanking on, I'm trying to remember, is did we... Yes, sorry. Long lesson, even I forgot what we did. I'll edit this part out. So since we created a function called valid transforms earlier that takes in an image and or an item and applies the validation transforms, we'll convert it to a tensor and pass in our image, and then unsqueeze it. And there's explanations in here, but essentially unsqueeze turns this into a batch of 1. Before finally passing it through the model, like I showed earlier, getting our predictions, decoding them, and getting our prediction and label. And this recreates some of what fastai does under the hood and starts to extract some of those layers. Lesson 5 will go much more in depth on this because it's focused strictly on deployment. So we have deployment with fastai and without fastai. Now there's 2 lessons in between here. So the next lesson we'll talk about different applications of vision. So multi-label, recognizing unknown images, a little bit on cross-validation and model ensembling. In lesson 4 will be on semantic segmentation. And then this lesson, other pre-trained models, is where we're going to start to dive in heavily on this idea of freezing and layers and layer groups and optimizers and how all of that intertwines with fastai. I just mostly wanted to give you a brief insight into it, throw a bunch of information at you, and then over the next 2 to 3 weeks, we'll start to solve some of what's going on. Now, before I round up the lecture, are there any questions on what I just did here? As I attempt to move my keyboard with the cat laying on it. you guys a few minutes. That was not what I wanted to do. We'll edit that out of the video. All right, so if there's no more questions, what I'll basically leave you with is technically it would have been better if you did it at the start of this lecture, but in the information channel, I have a poll for week 1's lesson. Please fill that out in the next few days. Once the edited video goes out, I'll be a bit more ahead this time and open a poll for week 2. So how this lesson did, any feedback, any questions, and so forth. But do keep in mind the whole point of this lesson is to make you feel like you learned a lot very quickly. It's okay to be a bit confused. Take a bit of time to sort of go over this code, run it, and really start exploring lesson 3, because lesson 3 is much more, I mean, I can just show you, for example, you know, it's very application based, like how the original Walk with fastai was. Today was mostly, I really wanted to get you used to, this is what the low level API looks like. This is what we can do without fastai and how that looks to strengthen those foundational layers that a lot of people who use fastai don't have and spend a lot of time getting there in a very confused mess. Speaking from experience. So thank you guys so much for joining. For some of you, I know it's very, very late. So if you stayed along this whole time, appreciate it. Otherwise, I'll try and have the edited video out by within a few days. I'll say it should take much faster than the first one did now that I've done it once. But thank you guys so much.